Okay, so today's assignment, up until this point, actually, pretty much everything we've done, maybe not everything we've done, we've been talking about physical changes, so heating it up, melting it, freezing it, boiling it. That's all medical, all physical changes. Okay, today we're going to talk about how to find the enthalpy associated with chemical changes. Okay, and there's a whole bunch of different ways to do this. It all depends on the situation you're given. Okay, so we're going to learn four different methods on how to do this, and I'm going to talk through them today. Feel free to ask any questions you have. Okay. So the first method is using these things called standard heats of formation. Okay, basically standard heats of formation are the enthalpy, or if you want to think about enthalpy as like the potential energy that each molecule has. Okay, these are given values. These are values that have been determined experimentally, and they're placed in these tables. So, for example, here's a short version of this table down here. So we have the compound and their delta H of formation right next to them. Okay, so CH4 gas, its delta H of formation is negative 74.8 kilojoules per mole. Okay, CO2 gas is negative 393.5 kilojoules per mole. Now you do have to be careful though, because the state of matter does matter. Okay, the state of matter does matter, because as we know, it takes energy to heat something up or cool it down, right? Turn it into a liquid or a gas. It takes energy, right? From a liquid to a gas, you need to put energy in, right? So the delta H of fusion for H2O liquid is negative 285.8 kilojoules per mole. However, the delta H of formation for H2O gas is negative 241.8 kilojoules per mole. Okay? So just keep that in mind. The state of matter matters. Okay, now how do we use these things? Okay, well, we use these things according to this equation. Don't get too worried and scared of this equation. What it's saying is the delta H of the overall reaction is equal to the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. Okay, so just be careful here. It's the products minus reactants. So products comes first, okay, and then reactants. Okay, so how do we do this? Well, we look for the delta H of the products. So for example, in this first problem here, number 1, NaCl is in the product side. Okay, so NaCl has a delta H of formation. So let's go down here. NaCl has a delta H of formation of negative 411.0. So negative 411.0, or just negative 411. And then we add to that the delta H of formation of H2O gas. Make sure it's the gas one. And H2O gas is negative 241.8. Okay, negative 241.8. Okay, so that's the sum. We add them together. This means the sum of. Okay. And then we subtract. So it's the products minus the sum of the reactants. Okay, now the reactants are NaOH solid. So let's see here. NaOH solid is negative 426.7. And HCl gas, so we have HCl gas, it's negative 92.3. Okay, so that's basically how you set it up. Okay, when you do the math, you should get the answers provided at the bottom here, or right here. So negative 133.8. Do be careful, because these will give you a negative number. This will give you a negative number. However, this negative will make this a positive. Okay, so do be careful with that. Okay, now let's look at the next one. So again, we have a reaction here. It's going to be products minus reactants. Just be aware this is CO2 and this is CO gas. Okay, and for CO, I forgot to put it in the chart, so it's up here. Okay, it's up here. Also, if you have a element by itself, elements by themselves are always 0, and all the diatomics are 0. So O2 is 0, but also what's also 0 is F2, N2, Cl2, Br2, I2. Those are all 0. Okay, so those are all 0, and then elements by themselves, lone elements. So like if you just have Fe or you just have Al, most of the time it's going to be a metal. So if you just have calcium, those are all 0. Anything by themselves is 0. Okay, so let's continue here. So this problem here, let's go up. So products, we have 2 CO2. So we do have to take into account the coefficients here. So there's 2 CO2s here. So we actually have to do 2 times the delta H of formation, which is negative 393.5. Okay, so that's the products minus the reactants, minus the sum of the reactants. So O2 is actually 0. And you don't have to write it if you don't want to. I'm going to write it here just because. O2 is 0. And we add that to the carbon monoxide gas. And here we have 2 carbon monoxides. So it's 2, oh my goodness, 2 times the delta H of formation of carbon monoxide, which is negative 110. Okay. So again, that's how you set it up. Don't forget that this negative and this negative, when you get them together, it's going to be a positive. So just be careful there. Okay, and you should get this answer. Okay, and then you have some practice here, 3, 4, and 5. You try those ones. Okay, next one. Next one is a little bit tricky and can be a little bit confusing. This one is kind of opposite. We have the we're looking at the bonds broken minus the bonds made. Okay, so the bonds broken are the reactants. Ooh, so this one is reactants first and then products. But it's a very similar process. So delta H of reaction equals the sum of the delta H of the bonds broken minus the delta H of the bonds formed. Okay, so for example here, you just look at the bonds in the reactants. So the bonds in the reactants here are HH and ClCl. There's one of each of them. Okay, and then you're going to go down to the chart here. HH is 436 kilojoules per mole. So you have one of those. So 436 plus ClCl. A ClCl single bond is 242 kilojoules per mole. This is 242. Then minus the products, minus the sum of the products. So HCl is right here, 431. And there's two of them, 1, 2. So we can just say 2 times 431. Okay, it gets a little bit trickier as we get more and more of these bonds here. You just have to make sure you keep all of them in order here, right? So for number 2, you in the reactants, you have these CH bonds, 1, 2, 3, 4. So you have 4 CH bonds. The CH bonds are 413, so 4 times 413. Plus, you have a CC bond, a C double bond. So that C double bond, you'll see that there's a CC single bond. That's the single bond down here. But there's also a double, and these are triples. Okay, that's a triple bond. Okay, these are actually different. This one is a double, this one's a triple. A little bit hard to see there. If I zoom in really closely, you can see it's blurry, but there's 1, 2, 3, and this one has 1, 2. Okay, you also notice that the more bonds you have, the higher the energy. Okay, so if two look the same to you, like for example here, this one, N, N, and N, N, this is double, this is triple. Okay, so just keep that in mind. So C double bond is 614. Okay, and we just have one of those. Okay, and then we also have an F, single bond F, which is 155. That's everything in the reactants. Then we subtract the products. You can see how this kind of gets confusing because you got to keep track of all the ones that you've accounted for. Okay. So CH, we have 1, 2, 3, 4 CH bonds. So it's actually the same as the reactants. And then we have CF bonds, 2 CF bonds. And CF are 485. So plus 2 times 485. And then we have a C single bond C, a C single bond C, which is 348. Okay, that's the setup. You just got to do the math there. The hardest part of this is just keeping track, making sure you have accounted for every single one of the bonds. It does help if as you do it, you can like just kind of go, okay, I did these ones. Okay, I did that one. Okay, I did that one. Okay, I did this, 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 this. That helps a little bit, but it also makes it a little bit ugly too. Okay, sometimes I'll label these. So this is CH. This is the C double bond C. This is the FF. This is the CH. This is the CF. And this is the CC. So sometimes it helps to label them that way so you keep track. Okay, so far so good? All right, so those are the first two methods. The next method is very tricky. This is the one that gives most people the issues. Okay. So this is where you're using something called Hess's law. And basically what we're going to do is we're going to take these three reactions, so 1, 2, 3, these reactions, we're going to combine them so that they make this reaction up here. When we combine the reactions, we combine their delta H's, we just add them together. And as long as these three reactions combine to form this reaction, then their delta H's, if we add the delta H's together, that will also give us the delta H for this reaction. Okay. However, sometimes these equations are not in the right order. So for example here, we have C2H6 right here in the product side. However, C2H6 here is in the reactant side. Okay, so what we got to do is we have to flip this reaction. So we're going to flip this one. Okay, so basically what we're going to be doing is we're going to manipulate these three reactions. Either we can flip them or we can multiply them by a number. Okay, and then combine them to form this reaction. Okay, so C2H6, in order to get that to be in the product side, we have to flip this reaction. So instead, we're going to get 2CO2 plus 3H2O yields C2H6 plus 7 halves O2. Now, if we flip the reaction, what do you think happens to the delta H? Well, that also flips. So now the delta H of the reaction is positive 1560 kilojoules per mole. Okay, so C2H6, it is in our product side now. And then we had a change in delta H. So then I like to just cross this out because now we changed it. So that's going to account for this C2H6. The next thing we need to account for the C2H4. And what you'll see is that the C2H4, it's already in the reactant side, so this is good. We don't need to do anything. We can keep it the same, just keep. Okay, and then the last thing we need to look at is this H2. So if you notice, there is H2 here. It's already in the reactant side. There's already one of them. So most likely we're good. We can keep it. Okay. Now these do tend to get a little bit trickier. This one's a little bit easy, but that's because it's the first one. Okay. Now, if we rewrite all of the reactions together as one reaction, so I'm going to write the reactants first. So C2H4 gas plus 3O2. And then I'm going to write this one, so plus H2 plus 2CO2 plus 3H2O. Okay, so that's all the reactants. And that yields the products. So I'm going to write all the products. So 2CO2 plus 2H2O. Oh, I forgot the 1/2 O2 here, didn't I? H2 plus 1/2 O2. My bad. You have to make sure you account for everything because we want to make sure that both they cancel out on the stuff that we don't need cancels out. Okay, so and I'll show you what I mean in a second. 2H2O plus another H2O. They're both liquids. Plus C2H6 plus 7 halves O2. Sorry for my sloppy handwriting here. Okay, so let's just see. We have what we need. So C2H4, we have H2, and we have C2H6. So that's what we needed. That is the reaction we needed. All this other stuff needs to cancel out. And when I say cancel out, I mean that we have to have, if it's on one side, it's got to be on the other as well. So for example, here you have 2 CO2 and 2 CO2. There's no need to write it. It's the same here and there. It doesn't change at all. Bam, bam. So those, we can cancel those out. Okay? For H2O, there's 3 H2Os here. There's 3 H2Os here. Those cancel out. They're opposites. Okay? Then we have O2. We have 1/2 O2 and 3 O2. That comes to 7 halves O2. And we have 7 halves O2 here. Those cancel out. Okay, so you'll see that in the end, we only have these ones, the ones that we need. Then in order to find the delta H of this entire reaction, we add up all of these delta H's. We add up all the delta H's. So negative 1411.11, and we add that one, and then we add that one. When we add these three together, we should get the answer down here, negative 136.8. Okay, let's do one more. Okay, this one involves the other thing we need to think about, which is if we have to multiply a reaction, we multiply the delta H. So again, this video will be posted online, so if you do need it to go back to, feel free. Come on. What's going on here? Oh, I moved it over. Hold on. Okay. Sorry, my computer's lagging a little bit here. It's working too hard. Okay, so let's look at this one. This one, I typically like to ignore anything that's in multiple problems. So a little hint here. If you see that it's in multiple equations, so you see that O2, see that O2 is here and O2 is here. We need O2 there. I don't worry about that because usually it works itself out. If it's in more than one problem, it works itself out. Same thing like N2, N2 here. Usually that'll work itself out. So I start with something that is only in one single problem first. So for example, let's start with NH3. NH3 is here. Oh man, so there's two things wrong with this one. It's on the wrong side, and there's only two of them. So what we're going to do is we're going to flip it and multiply it by 2. Okay, so let's do that. When we flip it and multiply it by 2, so multiply everything by 2. So we're going to get 4 NH3 yields 2 N2 plus 6 H2. Okay? And our delta H now is going to be opposite and multiplied by 2. So our delta H is now positive 2 times 91.8. I just leave it like that for now. because I don't feel like taking out my calculator. Okay, so that makes this one, we're good with that. Next one, let's look at the NO. So NO is here. It's in the product side, and there's 4 of them. Here it's in the product side, but there's only 2 of them, so we're going to have to multiply this by 2. So let's rewrite it. So we get 2N2 gas, because we're multiplying everything by 2. 2 times 1 is 2, right? And then 2O2 gas yields 4NO gas. And the delta H for this one now, it's still negative, but you have to multiply it by 2. So whatever that is. Okay. And now I like to just like cross these out because I know we're not using them anymore. So I don't get confused here. Okay. Then the last equation, I need to get the O2s, but again, like I said, I have multiple O2s. Usually those things work themselves out, but I do have to get H2O. So H2O gas, so this one I have to multiply by 3. Okay, it is on the right side, but I need to multiply by 3. So multiply everything by 3, get 6 H2 gas plus 3 O2 gas yields 6 H2O gas. And delta H is 3 times the original, which is negative 483.6. Be right back, 1 second. Okay, so again, now I can cross that one out. And I have my 3 equations here. And if you want to save yourself a little bit of time, you can just look to see if something is in the reactants and the products, it cancels out. So for example, you have 6H2 gas and 6H2 gas. That cancels. You have 2N2 and 2N2. That cancels. You have your, let me see, let's use this color. Sure. No, brown. You have these 2 here. They're on the same side, so they actually add, and you get that 5O2. Okay, and now if you want to make it look really good, you just, so that 6H2O is there. That 4NO is there in the products, so those 2 are in the products. We're good. The NH3 is in the reactants, and the O2 is in the reactants. So we're good. Okay, and then the overall delta H, you just add these all together. And then you should get that number right there. Okay, so this basically, you're just manipulating the equations. If you flip them, you change the sign. Okay, from positive to negative or negative to positive, right? If you multiply, then multiply the delta H. Okay? Combine them, make it the same as the original reaction, and you'll get the delta H. Okay, so that's the third method. The last method is kind of like using stoichiometry. The last method is kind of like using stoichiometry to solve it. So here, for example, there's an example here when 1 mole of methane is burned at a constant pressure, 890 kilojoules of energy is released. Calculate the delta H for a process in which 5.8 grams of methane is burned. Okay, so we have 5.8 grams. We got to convert that to moles first because the delta H was given in kilojoules. Okay, it says 1 mole for every 890 kilojoules. So basically the delta H for the reaction or the delta H for 1 mole of methane, the delta H formation for 1 mole of methane is 890 kilojoules. The delta H of the reaction is, according to this, the 5.8 grams, you convert that to moles, and then you multiply by the 890 kilojoules per mole. Okay? And it's negative 323. Now, if it's released, remember, if it's released, that means it's negative. If it's absorbed, that's positive. Okay, so number one, when 1 mole of carbon disulfide is formed, 89.3 kilojoules of energy is absorbed. How much energy is absorbed when 10 grams of CS2 is formed? So first thing, we got to convert this, because this is given in kilojoules per mole, so we need to convert this to moles. So 10 grams of CS2, 1 mole is 64, it's 76 grams. So 10 divided by 76 is 0.132 moles. And then also tells us that 89.3 kilojoules is released for every 1 mole. So you get 11.75. And it's absorbed, so it's positive. Number 2 says the production of iron and carbon dioxide from iron 3 oxide and carbon monoxide releases 26.3 kilojoules for every mole of iron 3 oxide. If 84 grams of iron 3 oxide react with excess carbon monoxide, how much energy in kilojoules will be released? So this is very similar to number 1. Okay, I'm not going to go over that one. Number 3, though, it says gasohol combusts with oxygen, produces 1368 kilojoules of heat per mole of gasohol. How much heat is released with 20 grams of gasohol reacts with 100 grams of oxygen? Okay, so this is a limiting reagent problem. Okay, so what you need to do is you need to take that 20 grams of gasohol, C2H5OH, convert it to moles. So the molar mass here is 24 plus 30 and 1646. That will tell you how many moles of gasohol there is. So let's see here. So 20 divided by 46, 0.435. Okay, and then you can multiply that by and in reality, like we can pause there for a second, because what I want to do is I want to see how much of this O2 is going to react with gasohol. So I'm basically going to do a conversion from oxygen to gasohol, because the heat of combustion is given in for mole of gasohol. So I'm going to take that 100 grams of O2, convert it to moles, so 1 mole over 32 grams. But then I'm also going to convert it to the C2H5OH. So there's 1 C2H5OH for every 3 O2. Okay? And that'll basically tell us how many moles of C2H5OH are going to be burnt with that much oxygen. So how much will the oxygen run out first, or will the gasohol run out first? And that's important. So here I get 1.042. 1.042 moles of C2H5OH. So basically what is going on here is that I have enough oxygen to burn this much C2H5OH. Okay, I have enough oxygen to react with this much C2H5OH, but I only have this much C2H5OH. So the oxygen is going to be in excess. This is excess. Okay, and when we have the excess, we're not going to use that one. We're going to use the limiting one. So this is the one we're going to use to figure out how much energy is released. So we take that many moles of it and we multiply by the 1368 kilojoules for every 1 mole. And when you do that, you should get this answer here. Yeah, pretty much. Okay, so that's a really tricky and hard one, but good luck with that. All right, so those are the 4 methods. Try them today. Try to practice them. There are some practice questions here. I've given you more practice tomorrow. So like you just have to practice number 2 for this one. I kind of just wanted to give you the examples today and try a little bit, but not get you overwhelmed with it. Just give it a shot. There'll be more practice for you guys tomorrow, okay? So give it a shot, see if you understand it, and then come with questions tomorrow. We can kind of straighten it out, and then you can practice that tomorrow. Okay, really I just gave you enough to kind of just get a general idea of what you're doing here. All right, and that's all I got for you guys today.